So you are welcome to the 17th day of UTME and WAEC 2022 Physics Examination Prep. Welcome to the topic of capacitance and dielectric, which is the second part of electrostatics. I am Engineer ED. This video covers maximum in-depth of knowledge in minimum possible time. Concept video for both basic level and advanced level are available on the MOST Academy concept checklist, which you can watch individually at your leisure. But this video covers all what is needed for you to pass UTME and WAEC based on the new pattern of examination, especially for the UTME student. We start with the first question. As usual, I'm going to be taking you through some other things you need to know with respect to the question for ease of understanding. What is the relative permittivity of capacitor if the capacitance with a medium as a dielectric is 16 farads and its capacitance in vacuum as dielectric is 2 farads? Yesterday, if you follow us through the course of electrostatic, I defined what we call dielectric in terms of epsilon naught. I said the dielectric, which is given in terms of our relative dielectric, I remember it was there, is given as epsilon naught, epsilon relative is equals to the 1 in medium divided by the 1 in vacuum. Now, to understand this, we have to understand the basic concept of capacitor. When we say capacitor or capacitance of a capacitor, we need to understand the basic knowledge is that when a quantity of charge that is flowing per unit potential, the quantity of charge flowing per unit potential is called the capacitance of a capacitor. That means if I have a conductor, then I'm bringing a charge, the charge from a particular point to a place inside the conductor. So to measure the total number of what we say the quantity of charge which I'm moving from one point is always proportional to the potential difference between it. So if we now iterate the constant of proportionality, I want to make it basic. I don't want to go into something that is so tough. We now introduce the capacitance, which we say CV. So this C is defined as capacitance, which is measured in farad. You can say C is Q by V from mathematics. So the capacitance of a capacitor is just a property of an electric field. Now we are still on electric field concept. We are only electric field. Why am I making mistake in spellings? Electric field. So keep it in mind that the property of an electric field in which a charge that is supplied to a conductor is producing a potential difference between its ends is called capacitance. So please always keep that at the back of it. It is now measured in farad. Like I told you, all these things are for point charges. And because it's a point charges, we measure capacitance in farads, just the short form of Faraday, which is denoted basically by F. Most times you see it in form of capital letter F. So the conversion still holds, which we discussed yesterday. So the conversion is always because they are in point charges, very, very small charges, elemental charges. So we say conversion, remember, as we talk, 1 microfarad is the same thing as 10 raised to the power negative by 6 farad. We talk about 1 nano, this is 1 nanofarad is 10 raised to the power negative 9 farad. And the last one we talked about yesterday now is 10 raised to the power minus 2, which is pico, 1 picofarad. So 1 picofarad is equals to 10 raised to the power negative 12. So conversions are always going to be needed when you are doing that. And remember, we have talked about electric potential yesterday, V, the potential energy, the energy involved in moving a unit charge from infinity to a point in an electric field. Remember the formula yesterday. If you follow us, you have to follow us day by day. Checklist or playlist are available for you to check. It's given by KQ over R. Remember, that is electric potential. We define this as electric potential, which was talked about yesterday, and we talk about K in terms of 1 over 4 pi epsilon naught, which is always constant, 9 times 10 to the power negative 12 farad per meter, or Newton meter per coulomb square. So now, guys, I am not going into that. I am just telling you that when you talk about capacitance, you talk about capacitance. Capacitor has various uses. They have a particular use. They have a lot of use that we use them. The performance depend on the type of capacitance. But for the nature of this question, I have talked about dielectric yesterday, which I told you, if you want to talk about dielectric, now to make a capacitor, what I'm trying to say now is that if you have a conductor, at least there is a conductor. I am just taking you through quick concept. What you learn for week in classroom are going to be taken in minutes here. That is the essence of most the academic physics channel. Classroom is the best. You have to go there, but you have to what? Do a quick revision with us, which it is what we are doing here. Now, this is two conductor. One will be positive, the other will be negative. This is a charge rod. When they are now separated by a distance, two conductor separated by what? An insulator. An insulator means material that do not conduct what? Electricity. I'm giving you shorty concept based on your level. In advanced level class, we have a lot of things which we talk about classifying capacitor. For now, I'm limiting myself with respect to what you are going to face in your examination. So when capacitors are separated by an insulator, this insulated body or insulator rather, insulator or insulated body are now called dielectric, which is what we are talking about now. Now, the dielectric are related in terms of vacuum. We write it as epsilon naught. And in terms of medium, we write as what? Epsilon n, you can see. So we now give it a definition which we call relative. So relative dielectric is now dielectric in medium divided by vacuum. The revision are available on most the academic physics page, which you don't need. The question for your WAEC and UTME are just direct, and that is the way it is being done. So directly, it is a very simple question. If you are following us with our day-to-day package, that is the best way. You start from the scratch. If this is your first meeting, you have to start and watch. You might have an idea, but I can tell you there are still some things you are going to be hearing for the first time. So here we said the medium values was given, the electric in media is given here as 16. If you read through the question, medium was 16. And the vacuum, which is always empty space, is 2. 16 divided by 2 is nothing but 8. So the answer to this question, my dear student, is nothing but 8. So the correct answer to our first question today is choice C. So that is the right answer, guys. We move to the next question. I hope students understand that concept. So let's move. This should not be a problem. There are just 12 questions which we want to solve with respect to your syllabus. Now, the next question is arrangement of capacitors. Now, in your classroom or in your junior classes, you might have studied that capacitors can be arranged both in series and also in parallel. Now, let me quickly talk about the most important thing. Permit my spelling if it is not correct. I do tell you, do write the correct spelling. Now, when capacitors are arranged in series, that means they are connected directly to the battery. So the line connecting them directly to the battery are just like this. We just take two cases. I just have to be fast because I have a time frame. I have a time that is allotted for this video, and I don't want to go more than the given time. So if we talk about capacitors that are arranged in series, I may not show the battery because of time frame. We use this double equal stroke. Wow, it will not be straight. That's just the problem about it. So now, that's the first one. When they are connected in series, we now define what we call equivalent capacitance. Equivalent capacitance of series. Now, this is a true equal stroke. Please note that they must be equal. They are now connected directly to a battery of V. I should just show that it's just time. Time is always a major constraint when we are doing this type of stuff. Now we have this, and we have the battery. You know, battery are not equal length. Definitely positive and negative. Then the stuff is close. So when the key is closed, it will move from what? negative to positive, which you might have studied. Your teacher will tell you when we get to the electricity part, I'll talk more about that, about the flow of current and stuff like that. So let's say capacitance C1 and capacitor C2 are in series connected to a potential of V. Now, what we know, when the key is closed down, it will move. It will start moving. As it moves, talking about capacitance, the equivalent capacitance, we define equivalent capacitance. We call it capacitance of equivalence. Now, equivalent capacitance, which is the total capacitance that we move in this one, is always very simple to do when you have capacitance arrangement in series. I will just start with this one and use that to explain the second one. For two capacitors are arranged in series, the equivalent, if there are two capacitors, is always C1, C2 over C1 plus C2. Always keep that in mind as what? Their quantity of what? Quantity of charge. Q, quantity of charge, or quantity of electricity, anyhow you call it, is the same. Q is same. So Q is same. Always keep down the one. The one that will flow here will be Q is equals to C1V. C1V, and the one that will flow into the second one will be Q equals to C2V. So you understand that the quantity of charge is the same. Always keep that one. So at the back of your mind. So the potential difference in what, when they are connected in series, are always not the same. So for two capacitors, the equivalent capacitance is always the product of them over the sum, in as much they are two. But if they are equal, you can also say the equivalent capacitance is equals to C by N, C over N. That means the capacitance that flow in one divided by the number of capacitors. For example, if this is 2 microfarad, 2, I'm just giving you an instance, and this is 2 microfarad. Simple way. Now they are equal, they are 2. Equivalence will be 2 over 2, which is 1. What is C? 2. 2 is the same to, they are equal. How many, where is the second 2? How many cells did I have? How many of the capacitor? I have 2 of them. If I have another one joined to it, just for illustration's sake, and it's 2 microfarad, now it is 3. It will now be the capacitance is 2 is equal over how many of them? 1, 2, 3 over 3. This will be the equivalent capacitor. So always keep that in mind, as C over N is always used to calculate the equivalent capacitance in a capacitor. So that is that about that. Then you can also use this one as well in series. There are 3. If there are 3, you are now expected to use the famous one, equivalence. If there are more than 2, then you use 1 over C equivalent. Equivalent means the total is 1 over C1 plus 1 over C2 plus 1 over C3. But if they are equal, you can easily use C over N if it is the same thing. But if they are different numbers, it's better you use it. You can also use product over sum, but in this time you have to know math. It will be C1, C2, C3 over C1 times C2 plus C2 times C3 plus C1 times C3. But that will be complex. That is why teachers prefer giving you this for equivalent capacitance for series arrangement. So I hope you can see this, which is the best method you can always use. And I believe you have learned this in your junior classes. So for series arrangement, this is the way you do that. And it's very simple. Therefore, parallel arrangement, I'm going to use this one for my parallel arrangement. Now, always keep it in mind now that for parallel arrangement, then I need to talk about the potential difference that is flowing. Potential difference flowing through series are not the same. So permit me to quickly clean this first slide so that I can use that to explain what I mean by PD flowing across series arrangement. Now we say for PD flowing across, I'm just considering 2 capacitors now. So I can say C1 over C2 is equals to V2 over V1. So always keep it in mind. This is the way we relate it because it's so simple. Or another way, if you have 2 capacitors connected in series, you want to know the PD across the first one. You can say the PD across the first one, I call V1, will be equals to the capacitance in the second one over the V, the total potential over C1 plus C2. Now, if you want to get the capacitance, the voltage in the second one, it will be the capacitance of the first one as C1 multiplied by the total potential over C1 plus C2. Keep this in mind because it's important. Most of the teacher will write it for you as C1 over C1 plus C2. It's more like a divider multiplied by V total. So this one is telling you the potential difference. If you have C1, it's telling you the potential difference in the second one. You can see C1 is equivalent to V2. C2 is equivalent to V1. So if you want to get V1, yeah, for the one in the first one, I want to get the amount of PD across this now. It will be equals to, in fact, in A-level classes, we use what we call a simple nodal analysis. But for your own level, because you don't need nodal analysis, I'm not talking about nodal analysis. I'm only giving you quick way because your exams are very simple and straightforward. So if you want to get the one that flow in this one, it will be in this one now, in C2. Now in C2 is C1. If you want to get the one that flow V1 here, voltage that will come here, it will be equals to what? The second capacitance over the addition of the two. If they are more than two, you follow the same way. Multiply by what? The V total. So this will give you the one that flow in the first what? Potential. So this is the way we analyze the amount of potential, because potential difference is not the same. Q equals to CV, we always hold for all type of capacitor. You can see what I'm talking about. I am able to break this thing down owing to the fact that you have learned something in your junior classes. If you have not learned something from junior classes, it will be difficult, and that is why going to class is very important for you to have an idea. So now with classes coming here, I'm going to help you break it down in a very short way. You understand? So back to what I'm saying. When they are now connected in parallel, that means they are not connected directly to battery, they are being bridged. Now what we say is that the equivalent capacitor is very simple. It's a simple topic. I know you guys have an idea about it very well. A very simple topic. Now equivalent capacitance, when they are connected in parallel, like this and this, now they are in parallel. For this type of question, the question before me is actually simple, but because I'm taking you through the what explanation, that is why we are taking it. So for them, always keep it that V is the same for parallel. V will be the same. The amount of voltage that enters into this one will be the amount of voltage that enters, but Q is not the same. So always keep that at the back of your mind. So be that as it may, we say equivalent for parallel it's just the addition of the total number, C1 plus C2 plus, you understand, you continue to infinity. So it is very simple to do parallel because we just add them together as many as they are. So remember, like I said, voltage is always constant. Voltage is same. So V is not changing. So we always apply your Q equals to CV, and you are going to get all what is needed. So that's that. If our voltage is constant, so if Q equals to C, you can say C1V, then the other one Q equals to what? C2V, because voltage is the same. So you always use that to get the value. So let's come back to the question. I think the question is direct. So because it is direct, you can see these and these are connected. So if you want to use shortcuts, if they are the same, you can also say equivalent capacitance for parallel. If they are the same, it's just NC. It's just NC. N is what? The total number of cells, or the total number of capacitor multiplied by what? The capacitance itself. So now, for this now, I can say this is what? Equivalent capacitance will be parallel is 2 and 2. You can say 2 plus 2. So 2 plus 2, this is the line joining them. You can say a line joining, adjoining line joining the two. So 2 plus 2 will be resolved. When you resolve 2 plus 2, it will give you 4. So the 4 here now is now connected in the line with this, which is now in series. Now, in series, we said is series for 2 capacitors in series. We use this. Now, equivalent will now be C equivalent. Will now be, what's the first one? Now, the first one is 2 times the second one, which is the answer for these two, which was 4 over 2 plus 4. Direct way, you can always do that. It's very simple. That is 6 over, I said 6, 2 times 4 is not 6. You can always correct me. 2 times 4 is 8 over 6. 8 over 6 is the same thing as 4 over 3, which is 1.33 repeating. So 1.33 microfarad. 4 over 3 is 1.33 from calculator. And that one will make our second answer to be B. So always keep that at the back of your mind. Capacitance can be arranged in series and it can be arranged in parallel. And when we have both series and parallel, we call it a capacitive circuit. So which we use our Thevenin node analysis, not Thevenin's principle, node analysis to solve. So don't worry, we are going to get there. The next question will be on the next slide. We have 12 questions. This is just the third one. Now I can solve question because now we have the same thing. The resultant capacitance we call equivalent capacitance is what we need here. Now to get the equivalent capacitance of this, we just have to say the line I joining these two, just like what we did the other time. To solve this one, this is parallel. 2 plus 4 is going to give me 6 microfarad. So you can see the line up, there are many. So 1 over C equivalent is now 1 over the first one is 2 plus 1 over the second one is 3. The third one is now the one I've resolved, which was 6 plus 1 over the fourth one is 4. We go by for LCM. From LCM of all these things should be 12. 2 6 are 12. 3 4s are 12. 6 2s are 12. 4 3s are 12. That is equals to 1 over C equivalent. From simplification, and say 1 over C equivalent is equals to addition of all this is 10, 12, and 15 over 12. I hope I am not mistaken, 15 by 12. And you know, if this one cross multiply, if you turn it over, C equivalent, we also turn what you have here over as 12 over 15. I have only done what you call cross multiplication from you guys that you are mathematician, but for relationship of ratio, when you flip this also must flip up. So 12 over 15 in lowest time is 3F4, 3F, 3 times 4 is 12, 3 times 5, 4 over 5. And 4 over 5 should be 0.8, 12 over 15, 4 over 5 is 0.8 microfarad, as we are working in terms of microfarad. So guys, that is the way you do that. The next question is also talking about equivalent capacitance. The academy team are giving us much question on equivalent capacitance. And for this type of what we call them ladder capacitor. Now, to understand the concept of ladder capacitor, wait till when I get to concept of electricity, which is a course on its own. You should know when I say the course on its own, it's very right. So this is a ladder capacitor, or what we call ladder resistance. But to understand this, I'm not going to waste your time. I'll just give you the short way to get how to connect this. Normally, you can continue to add to it. That's why we call it infinite ladder capacitance. Oh my God. It's a simple question, but this is the way you start. It's an open circuit. You can see it's not connected to any battery. No battery, just like this one as well. But look at this now. This is the way we interpret. Now, when you have ladder, because you are connecting it like this. So the line joining the 2 points are considered to be this. Because if I bring the line, this is the line. So this particular one, I will ring it out for you. And this one, the truth is, there are other methods I can use to solve equivalent capacitance and equivalent resistance. There are a lot of methods. In fact, I have done a lot of A-level questions on electricity on my channel, which, you know, if you actually want to know how to do it, because there are some complex, these ones are not complex. To be honest, they are basic. So my point here, not to waste time, is this and this, my dear students, are in parallel. So, and you know, if the line joining these things are coming, you know, I told you, you are joining it like this. So this one coming in between parallel, just like this now. So this is the line. The line is a straight line. So this one that is coming in between are parallel, which when I resolve anything that is parallel, is going to be in series, just like what you've done here. So these two are in parallel because they are added like this. If you add another one, anyone is in parallel with the line that is coming. So this is, I will now resolve this. As I resolve it, I'm resolving this one in form of a way that they are now going to be in series with what? So if I resolve these two, I will talk about equivalent parallel, it's just addition. So for these two parallel lines, it is equivalent of the parallel circuit or parallel diagram, circuit given, which is also circuit, the way it is being called here, 1 plus 5. And 1 plus 5 in microfarad is 6 microfarad. Now, I can now redraw it so that you can now see the way it is now. Now I have something like this. Place diagram not on to scale. The line of the first one is 4. Then the one I have resolved now, 1 and 5 gave me 6. Then the last one, you know, it is like this. It's coming like this. The one I resolved now is coming to this point. So, but if I want to take this, and this, normally if they are more than 2, the 3 are in parallel. So now I have resolved it in series, and I'm having something like this. As I've redrawn it, this capacitive circuit. So I have 4 here. What do I have here? I have 6 here, and the last one I have 4 here. So it's kind of very simple to solve like this now that I have resolved it. So I will now use the same formula I have used upstairs there, as 1 over C equivalent is equals to 1 over C1, which is 4, plus 1 over C2, which is 6, plus 1 over C3, which is 4. So on simplification, LCM is still 12. 4 3s are 12, 6 2s are 12, 4 3s are also 12. My writing pad is hanging. It's really hanging. I just hope you guys are still hearing me. Thank God it's back. So 6 2s are 12, then 4 3s are also 12. So on simplification, C equivalent. I don't think I need to disturb myself now. Now you understand. You are going to flip the answer because this is 6 plus 2, 8 over 12. It will be 12 over 8. We've talked about that before, microfarad, which you can put in lowest time. 4 3s are 12, 4 2s are 8 microfarad. 3 over 2 is always 1.5. So choice answer to this is 1.5. That is the right answer to the question. I hope students are getting this. We move to question 5 and 6. Well, about question 5 and 6, we have also talked about this type of question is a capacitive circuit. They said in the network shown, determine the potential difference across the 5 ohms. You can see what I told you. Talk about C1, C2, right, and what C3. The battery is connected directly towards C1, but not the same potential we flow through. I have told you, I want to calculate the amount of what that voltage that flow through what C1 in this case, which is the 5. And I told you it is always C2 over C1 plus C2 times what? The total potential. I talked about that the other time. Will be what? The one that will flow in V1. So directly, I don't need to waste my time. What is C2 now? 15. All answers. I'm working in terms of microfarad. Shortcut, that is why you are mostly academic. C1 plus C2 is 15 plus 5. 15 plus 5 are 20. Multiply. What's the total PD? You can see are connected across it is 24. On simplification, I should get 5 here 3, 5 here 4, 4 here 1, 4 here 6, 6 3s are 18 volts. 18 volts will flow through this. The remaining 6 or whatever, 18 minus 24 is 6, and the 24 will be flowing through 20 ohm resistor or 20 microfarad. So guys, the answer to this is what? 18 volts, and that is the question answer to that. So keep it in mind, Mostly Academy will help you to get answers to question without wasting time. The next type of question says a 250 microfarad parallel plate capacitor are connected in series. A combined capacitor is then connected across 100-volt battery. The charge on each plate is dash. Now, they are parallel. Since they are parallel, it's equivalent capacitance. I may not draw because it's a simple question. We can visualize with what we see as they are in parallel, 2 of them. So you have to add 50 plus 50. I hope you understand, which is 100 microfarad, which we have discussed. Now, they are now connected across with what? 100 volt battery. That means the PD, the total PD, V total is what, my dear student, is 100 volts. So the question said the charge in each plate. Now, we said for capacitor, Q is always equals to CV. For capacitors, Q is equals to CV, whereas C is equals to the charge. So we are looking for the charge. C is equals to Q over V. I hope you are here. So on simplification, the total is 100. I hope you can see. Then I have to convert. I told you about this the other time. This is 10 raised to power 2 is 100. And multiply by 10 raised to power minus 6. Hope you understand, as microfarad is 10 raised to power minus 6. So directly we can write this as 10 raised to power negative 4 farad. It's important because of exam. So now this will be 10 raised to power minus 4 and not what I have written, because my Q, I've changed it now. I've converted to it farad. 10 raised to power negative 4 divided by 100, which is 10 raised to power 2. You have learned that when this one comes up, it will change to negative. So that's 10 raised to power negative 6. And if we talk about 10 raised to power negative 6, charges are measured in what? In coulombs. So if you want to write 10 raised to power negative 6, you can write it as 1 times 10 raised to power minus 6 coulomb. because you guys are used to calling it -6, while I'm used to calling it -6. So please, that is that, and that will be the answer to that stuff. And I think none of the option here is correct. If I have solved well, if I don't make mistake, that is what we are supposed to have. So I think there's an error here, or basically, I think this should be -6. So I think this should be the answer. So please keep that. I think there's an error in typing. So this should be the correct answer to that. And that's that about that. We don't need to waste time on what you know that you are correct. We move to the next question. Now, the next question says, let's quickly talk about this one. A capacitor of what? A capacitor, 8 microfarad. You know, you have to convert. So that is, the C is what? The capacitor has a capacitance of 8 microfarad. That is 8 times 10 to the power -6. I hope by now you know how to convert farad. Now, it's charged with potential of 100 volts. Voltage V is equals to 100 volts. The energy stored in capacitor is dash. Now, let me quickly let you know how they come about energy stored in capacitor. Now, I told you we define the capacitance of a capacitor in terms of the quantity of charge is equals to CV. Famous formula you might have learned. So when we make C square formula, we say C is equals to Q by V, which was the definition we give to capacitance of a capacitor. Now, to understand how they come about the potential difference, when we talk about charges under charge, we said the work done in bringing a charge from infinity to a point inside the what? Inside an electric field. You know, we have an electric field. This is a conductor. There is a charge here, a charge of plus Q. I'm using my energy to bring this charge from this point of infinity. It's placed at infinity away from the what? The metal sphere. You know, charges are always concentrated outside. There is no electric field in the uniformly distributed sphere. We've talked about this yesterday. So now this is just simple cases. Now the potential difference, the PD, which we call electric potential V, is the amount we said. You have to understand this. Is the work done. Work done. When you do work, energy is required to do work. Under the concept of work, energy, and power, we've talked about this. So we say the work done in bringing what? The work done in bringing a unit positive charge from infinity to a point in an electric field, which we talked about yesterday. We have told you about electric field is 0 for uniformly distributed. Now we say the PD is now equals to the work done in bringing a charge of plus Q. Potential difference, which we call the what? Electric potential difference, is the work done over in bringing a charge. Work done over charge. So if you want to make work done subject of formula, then we come about the famous formula of the work done in bringing what? A charge is equals to the product of the charge multiplied by its potential difference. Now, from the famous formula of capacitor, Q equals to CV. On seeing Q here, put CV. You say work done equals to what? CV squared. Keep it in mind for the work done. Now, when work is done, the total amount of work that is done is now given by the famous formula of CV squared, which you are going to use in a lot of questions. Now, it is not always going to be a uniformly distributed sphere. Now, if you now talk about energy, you say energy is required to do work. I hope you understand that. Now, initially, there is a potential energy. Every system of body has interactive potential energy in it. So a potential energy we denote by U. So if you want to move it, there must be a force that is greater than that of the potential energy to drive the what? Potential energy to kinetic energy. Concept of work, energy, and power. Now, I'm not going to waste your time. We now say the total energy required will now be work done minus the initial potential energy. I hope I am communicating. What is the work done? CV squared. What is the potential energy? Now, energy is always given as half CV squared. So how is half CV squared coming from? It's so simple to know. Anything you want me to derive for you, because I derive the formulas on my channel. I don't just use them. If you integrate both sides here, integrate this one. For those of you who follow my chapter from the beginning, integrate this. Now, from here, you know this is raised to power 1 plus 1 is what? 2. And over 2, it will give you CV squared by 2, which you write as what? 1 over 2 CV squared. So this is the energy. So the potential energy of the charge. So if you remove the work done minus the initial potential energy, it's just like saying 1 minus half. What is 1 minus half? It's still going to give you half CV squared. So we say the energy, interaction energy required to move what? A capacitor, a charge of a capacitor to a point inside the electric field is always given as half CV squared. Basic, whereby the work done is equals to CV squared. Work done is CV squared, energy equals to half CV squared. Let it be known, because these are technical questions. You can, and you know, energy can be converted to a work energy theorem under the concept of what's that. So it's a simple question, no need to waste time, but because I just want you to see how it is being done, you can say energy is equals to, now we say half CV squared. Another person can write it as half QV. If you want to write it in another way, E is equals to half UV, because it's the work done too. You can see. So QV. So anyhow, both will give you the same answer. It depends on the parameter that is being given. Here we are giving C, we are giving V. So I think this is the best to use. So energy is now equals to, directly, you can just put the values. Energy here will be equals to 1 by 2, which is half, times charge is 8 times 10 raised to power. Capacitance is 8 times 10 raised to power negative 6 times 100 squared. That is 100 times 100. That is 10 raised to power 4. If you don't know 100 times 100, write it 100 times 100. Let me teach you how to multiply numbers. How many zeros? 4 zeros. Then 1, then 4 zeros. So which is same as 10 raised to power 4. Do you understand? So I will just write as 10 raised to power 4. So I will just cut 2 here 1, 2 here 4. So you just need to be careful, because all what my students are typing here, I don't know, they are just typing rubbish for answers for us. So this is 10 raised to power 4. 100 times 100 is 10,000. This is 2 here 1, 2 here 4. So this is 4 times 10 raised to power 6 minus 4. Minus 6 plus 4 is minus 2. 10 raised to power negative 2 joules of energy. So this is the answer. And I don't know why they find it difficult to put raised to power. And I will fight them for this anyway, but that is not for now. So it should be minus 2. I'm sorry about all these guys. Apologies for all this, because it's not going to make sense for us to be changing answer when we know we are coming online. So sorry about that. So that is the way you do that. Please keep it in mind. Half CV squared. If you don't know how to cut, do it directly the way you understand. The formula is always half CV squared or half QV. So keep it in mind. Very important as you move forward. The next question, time is not on my side. Which of the following material is not suitable as dielectric material? Now, when I introduce you to the topic, I have talked about this too. So in continuation to what we are talking about, the next question is, which of the following materials is not suitable? Let's reduce the size. It's not suitable for dielectric material. I think there's an omission. Like I've said, dielectric materials are insulators that are basically used for separation. Because they are insulators, we use, I told you that they are like this. They are represented by epsilon naught. And we use anything that is an insulator. You don't use conductor to separate two conductors. So to produce a capacitor, dielectric materials are basically insulator. So your line of action is just what we have done. When we're talking about electrostatic charge, talking about paraffin wax, ebonite rod, polyethylene, and here we have glass. All these, none of this option is correct. Please note that none of this option is correct. I think the option as omitted option C. Look at me. I'm not the one setting all this question. So option C will be, because this is A, B, D, E. And I've never seen that kind of alphabet right from my childhood. So guys, what I'm saying is what all these are used as what? Dielectric. The question is none. No. I told you, when you know what you are doing. So the option should have been something that is a conductor. All these are insulators. So all these are used as what? Dielectric. So none of the option. So the option to this question will be C. As you can see, it is what there is an omission from what I think a typo error, which is from the Mosaic academic team. So guys, that is the answer to that. I hope you understand. We move to the next question. Next question is still on what we have studied. The energy stored in capacitor of capacitance of 5 microfarad is 40 joule. Calculate the voltage. We've done about energy. We have talked about the concept. It's half CV squared. So this time around, energy was 40 J. J means joules. Joules heating effect. 1 over 2 times, you know I will convert this to farad, and that is 5 times 10 to the power of negative 6 times V squared. On simplification, you can cross multiply. 40 twos are 80, and you can cut this one if you want to cut, but I just prefer to cross multiply. We have 80, this thing is loading again. Just have to be patient. We are almost there. 80 is equal to, I'm rushing now, is equals to 5 times 10 raised to the power negative 6. I just want you to say V squared. For my way, I told you that you can cut 5 here, 1, 5 can go in 8. How many times? 5 here, 1, 5 in 8 is 1. That is 16. So you can just say, basically, your answer here is V squared is equals to 16 over 10 raised to the power minus 6, which you can write as 16 times 10 raised to the power minus 6 returns to plus. So V squared, and what you need is V. So V will now be square root of all this. Square root of 16 is 4. Square root of 10 raised to the power 6 is 10 raised to the power 3. I hope you understand. And if you don't understand, use your scan calculator for UTME, and your WAEC student, you can use your normal WAEC calculator to get the answer. 4 times 10 to the power 3 joules, which is simple as 4,000. I said joules, volt. We are calculating voltage, and that is the answer. Then this next question is, the diagram above shows a closed square surface or box of 0.5 meter. That is the length. You say the area of the box, you can calculate the area covered in a uniform electric field E in the direction shown by the arrow. The direction is pointing out. You can talk about this what positive charge. I hope you understand that. What is the flux? Now, let me be able to define what is called flux in an electric field. We talked about electric fields yesterday. I think we didn't talk about flux. Like I said, UTM and Y questions are simple. I need to be fast with respect to this question. I think this is the last set of questions. You can just say flux, just write for writing. Say flux is a group of field, field lines. Because the field lines passing through an electric field, passing through. Let me just use a quick one. A surface. Let me use that. A group of what? Line passing through a what? Surface. You can see these are lines. They are passing through the surface. So it is noted by the symbol phi, and it is given as EA. That is the electric field. In terms of electric field, and electric flux is EA cos theta. The derivation are available on our page. Now, A is the area cover in which the line is. So now, according to the man called Gauss, there's a man called Gauss. He was the one that actually gave us the knowledge of this. He was able to tell us that some people say ES cos theta, where S is given as when we say S, we are talking about the surface area. Please note that. So to get the flux basically for on a non-uniform field, you don't need it. It's always the integration. Please always get that we integrate EA cos theta. But for now, I will only limit myself to this. Now, according to Gauss, what Gauss actually said with respect to this, I have to move fast. I'm very, very slow. I have just few minutes more. He said for any closed surface, that is what you just need for a level. For any closed surface, write down for any closed surface, a surface that is enclosed surface, the flux out, the amount of flux that is going out is always equals to the amount of what? The charge that is enclosed, divided by epsilon naught. By now you know what we call. So we always represent, in fact, if I go through Gauss law, because in A level we talk about this, but for you guys, you don't need much. We always represent it with a constant of 1 over epsilon naught, which is always the way we talk about the amount of what? The amount of what flux going out and amount of flux going coming in. So basically, flux is equals to electric field times area. If it doesn't have an angle, if it has an angle, flux is equals to electric field times the area multiplied by cosine of the angle. Keep it in mind because of new question pattern. So what I mean is simple man angle is that this is a constant. So what this man is saying is that the amount of flux going out for an enclosed surface is always equals to what? The amount of what? The charge that is flowing through it. So it's always constant. And when it is constant, it's always equals to what? 0. When the amount of one going out is similar to the amount of one what that is enclosed coming in, we say the amount of flux that is flowing through an enclosed surface is always what? Is 0. Because an enclosed surface that is uniformly distributed, I said the electric field in a closed surface, remember that there is no electric field in closed surface, is always equals to 0. So the answer to this question, because we are told there is a closed square box, closed square box, the answer to this is what? Nothing but no electric field inside a closed surface of a uniform what? Of a uniformly distributed or sphere or cube or anything, and that is what we are talking about. I hope you get that. Maybe I should stop here. See you guys tomorrow. Let me see if I have another question. I think I asked them to compile 12. If there's no other question, maybe we stop here. I think we take a pause here. Maybe that is all because now I cannot see anything. Maybe this stop is hanging. Oh, we still have two more. Maybe you guys just do this two because it's direct. What is the total capacitance for these? These are connected in parallel, C1 plus C2 plus C3. You've done that, very simple. Last question, parallel plate capacitor. Why are you guys giving this now? Now, I have to explain. Now, for the capacitance of a parallel plate capacitor is equals to absolute naught A by D. Please keep this formula in mind. This is the formula used for parallel plate capacitor. Absolute naught is the electric area and distance of separation. So when you increase the area, you are increasing the parallel plate, the strength. When you increase the distance, you are reducing this. You can see inverse to distance. But this one, when you increase the dielectric, you are also increasing the capacitance. It's because it's direct. Please keep that in mind. Increasing dielectric is also increasing what? Capacitance. Capacitance is direct proportional to what? Dielectric. For parallel plate capacitor, this is what we use. Capacitance is equal to absolute naught dielectric A divided by what? The area of the plate, distance of separation. So use this to solve this. You are looking for capacitance. You are given every other thing you need to know. Now, I don't like the people that prepare this slide because they are not taking what is important into details. Absolute naught must be given in this type of question. It is always given. Please just use it as 9 times 7 to 9, please, guys, because this should be a direct question because we're going to see it during the exam. If you are writing question, please always help us write it in full because errors will not make us understand full concept, especially for other students. So by and large, my point is I am stopping here because of time. So substitute the value. Area is given, distance is given, free space is always a constant. Permittivity, or you call it dielectric, is always constant. So you use that. See you guys soon. I'm sorry, guys. See you soon. Bye bye. And you have a wonderful time. Tomorrow we move to the next topic of magnetism. Bye for now.